Continue on the discussion about acid-base by discussing specifically the acid-base properties of water. If you remember, in a prior video we had talked about the ability of water to act as both a base or an acid. So when water is being mixed with an acid such as HCl, water ends up accepting a proton, so it acts as a Bronsted-Lowry base. And when water is paired up with a base, something that would pull off a proton, then water ends up donating a proton and acts as an acid. So the ability of water to act both as an acid and as a base causes water to be called amphoteric or amphiprotic, which just means that it's able to both donate and accept a proton. This happens also when water is on its own. So if you look at a pure water, so the water molecules could act in one portion as an acid and another portion as a base. So if you have two water molecules next to each other, there could be a proton transfer reaction occurring, resulting in the formation of H3O plus and OH minus. Again, one of them will be giving away H plus to the other one. Because these ions are present in water, that allows us to determine what we call the acidity of water. In this case, because water has equal quantities, equal concentrations of both of these ions, water is what we call a neutral solution. If you make measurements, you can find that the concentration of both of these ions are exactly 10 to the minus 7 molar. So it's a very small concentration, but it's there. And they're both at 10 to the minus 7, so that's what a neutral solution is. The way we do this measurement is by measuring something called the ion product of water, which has the symbol Kw, and that ends up being 10 to the power of negative 14. When we take a square root of this, it ends up giving us 10 to the minus 7, which is how the concentration of these two species is determined. Now, in this class, we're not going to go into the details of how to do that, but that's how the 10 to the minus 7 number comes about. More importantly, what you want to know here is that we would call any solution where the H3O plus or the H plus, remember H3O plus and H plus are the same thing, where the H plus concentration, the OH minus concentration are equal, we would call that a neutral solution. Specifically at 25 degrees, both of those concentrations would be 10 to the minus 7 molar. Now in acidic solution, remember acids are proton donors, so that means you're going to have something that will produce protons beyond what water would do. So if the new species you put in puts in a lot more proton, then your proton concentration will end up being higher than your hydroxide ion concentration. So if that's the case, then this is an acidic solution. Now, even though the H plus and the OH minus concentration is not the same, it turns out that as long as that solution is still in water, the Kw, ion product constant of water, is still going to be 10 to the minus 14. So this actually allows us to calculate the specific concentration of either H plus or OH minus depending on whether we know one or the other one. So for example, if our acid is 10 to the minus 4, that means the hydroxide must be 10 to the minus 10 because the product of the two has to equal 10 to the minus 14. So again, in this case, if H plus is higher than OH minus, you're going to have an acidic solution. Vice versa, if you put a base in water, the base is going to produce hydroxide, so now your hydroxide is more than what you originally start with. Your H plus is then also going to decrease, so overall what you're going to have is your OH minus concentration being higher than your H plus concentration, and that means that you have a basic solution. Similarly, though, the Kw still stays at 10 to the minus 14, so you can calculate how much the concentration is of each of these ions. So if you have 10 to the minus 9 molar of H plus, that means you're going to have 10 to the minus 5 molar of OH minus, and the product of the two is still 10 to the minus 14. Notice that in this case, 10 to the minus 5 is a bigger number than 10 to the minus 9, so there's more OH minus than H plus. So the way we're going to figure out whether a solution is acidic, basic, or neutral is we can calculate the H plus and OH minus and then just compare those two values. Now, a slightly easier scale is used in practice. Instead of looking at the actual concentration of H plus and OH minus, we look at something called the pH and the pOH scale. And more specifically in practice, we just use the pH scale. And the way this works is the following. It's often confusing to look at a number like 10 to the minus 9 and 10 to the minus 5 because, the habit of people is that, the bigger the number, the bigger the value, right? But with negative exponent, of course, that's different. The bigger the negative exponent is actually the smaller the number. So a guy by the name of Sorensen invented a scale that converts these negative exponent numbers into a positive number. And the way he does that is by creating something called a pH scale, where pH stands for the negative log of H plus concentration. So if you have a something like 10 to the minus 9 H plus, to convert that number to pH, all you need to do is take the negative log of 10 to the minus 9. Now, if you enter that in your calculator, what you'll see is you're going to get the number 9 as a result of it. The interpretation of the pH scale is shown here. The way you do it is the following. So if your H plus is 10 to the minus 7, remember that's what a neutral solution would have. So that means your pH is going to be negative log of 10 to the minus 7, which ends up just being equal to 7. So any solution then with pH equals 7 would be considered a neutral solution. An acidic solution, as we said, is a solution where there's more H plus than what you expect in water. Water has 10 to the minus 7, so then more than 10 to the minus 7 means a number that's greater than that. So let's say you think about numbers like 10 to the minus 6 or 10 to the minus 5. Those are all numbers that are bigger than 10 to the minus 7. If you take the negative log of those numbers, you will get a pH that's less than 7. So pH less than 7 corresponds to an acidic solution. Vice versa, if you think about solutions that have H plus less than 10 to the minus 7, their pHs would end up being greater than 7, and so pH of 8, 9, and so on would be considered basic solution. So here's a quick example. Let's say your solution has a concentration of H plus being 3.45 times 10 to the minus 5. If you want to know what kind of solution you have there, all you need to do is calculate the pH, which is just negative log of that number, 3.45 times 10 to the minus 5. And what you'll get is 4.46 if you plug that into your calculator, and 4.46 is less than 7, so that's going to be an acidic solution. Sometimes when you want to calculate pH of bases, a lot of times you're going to need to calculate something called a pOH, which is just the negative log of OH minus concentration. So that letter P corresponds to the mathematical operation of taking a negative log. We don't use this as often as pH, but again, like I said, sometimes this is used in the calculation of bases. So a neutral solution then, its OH minus would still be 10 to the minus 7, right? So its pOH is going to be 7. An acidic, though, means that there's less OH than what you would expect. So the OH minus is less than 10 to the minus 7, which means the pOH would be greater than 7. And vice versa, a basic solution is going to have OH minus greater than 10 to the minus 7, which means its pOH is going to be less than 7. But again, we look at pH values when we determine whether a solution is neutral, acidic, or basic. But you do want to know how to calculate pOH, which is done by taking the negative log of OH minus. Now here's the part that's useful though. Remember I said earlier that the Kw is always constant, and matter of fact, the Kw is just the product of the H plus times the OH minus concentration. So you can derive a formula that looks like this by taking the negative log of both sides of this equation. Remember, keeping in mind that Kw is always 10 to the minus 14, so if you take the negative log of 10 to the minus 14, you get 14, and negative log of H plus is just pH, and negative log of OH minus is just pOH. So then that tells you that pH and pOH always adds up to 14. So if you know the pOH value, you can calculate the pH value, or if you know the pH value, you can calculate the pOH value.